Hi everyone. My name is Howie, and talk is Better Scala builds with the mill build tool. I've been an open source developer since 2012, many libraries in Scala. Apart from the open source Scala work, I've also done a lot of work at companies like Dropbox and Databricks, largely focused on the developer tools and testing infrastructure. So things like your cloud dev environments, your CI/CD systems, your test frameworks, integration testing systems, and so on. I'm the author of the book Hands-on Scala Programming. So if any of you need a book to learn Scala or need a book to recommend to someone else to learn Scala, Hands-on Scala Programming is a great way to get started. Um, and this talk about better Scala builds with the mill build tool has three sections. First, we'll talk a bit about what is mill. Then we'll talk about why you may be interested in this new mill build tool. Then lastly, we'll go into some details about how mill works. And from there, you can learn about what really makes this build tool tick internally. So first, what is mill? So mill is an open source JVM build tool. It's actually not that new a project. It started in late 2017, originally targeting Scala, but more recently has grown support for Java, support for Kotlin. It's currently in the process of getting support for Python and JavaScript and other platforms, Android. It mostly does the same thing as SBT and Maven and Gradle, but aims to be better, easier to extend, easier to use. The performance is pretty good. It's 4 to 10x faster than Maven, 2 to 4x faster than Gradle for equivalent builds on our benchmarks. And it's used by quite a lot of Scala projects, not the older ones which are still on SBT, but a lot of the newer projects that you probably have come to rely on. So if you use SBT, you're using Corsair, the dependency resolver. Many of you are probably using Scala CLI. One not less, I guess, famous part of the Scala ecosystem is the Scala hardware design area. So Chisel, Spinal HDL, all are using the mill build tool these days. And of course, all of my libraries in the ecosystem, Ammonite, OSIP, FastParse, these have all been using mill for 5, 7 years now. I haven't touched SBT for literally more half a decade, and it works great. So mill is pretty well battle tested in the community and in the wild. If you want to learn more, there's documentation at millbuild.org. I won't go into all the details in this talk. There's a lot more stuff there, how to get started, how to use it, and so on. So first, let's do a small demo. So over here, I have a terminal. Over here, I have my small Hello World mill build for small Hello World application. So this is a build.mil file. This is equivalent to a build.sbt, build.gradle, build.bazel, and so on. Mill build files are written in Scala. And you can see there's a package statement, there's imports, you have an object foo extend Scala module. So foo is a module. We declare some configuration like Scala version is 2.13.14, IV depth is Scala tags and main args. And we have a test suite, which is nested within foo. So it's foo.test. And it has its own dependencies and its own test framework configured. So from here, I can do mill foo.compile. I can do foo.test. You can see I run a small test suite internally. If I go and break the test suite, you can see the foo.test fails. I can do foo.run. It's asking for an argument. Let's say dash text hello. You can see if say it outputs a hello there. I can do mill foo.assembly or mill show foo.assembly to show me the generated file. And this is already a self-executing assembly. You can run it outside of the mill build tool. So this is kind of just a hello world of what mill is like. This is a small demo application, just parses some command line arguments and renders a bit of HTML using Scala tags. But it's just meant to show you how you can define your mill build using normal Scala objects, normal Scala traits, normal Scala definitions, imports, and so on. And that's enough for you to build your program. So back to the slides. So far, nothing we've looked at here is that surprising, right? You can compile, test, run, package assemblies, and run them up later. But the question is like, why mill? So you can already do all this using SBT, using Gradle, using Maven, Bazel, Pants, whatever you name it. So let's look at why you may want to use mill rather than the alternatives. So there are three main reasons for this. One is that mill is in many ways much more foolproof than many of the alternative build tools out there. Two is that mill has a lot of support to help you with understandability of the build and understandability of the project structure. And lastly, mill is much more easily extensible. So you can just write code to extend your build. You all are Scala developers, you know how to write Scala code, and Mill lets you write Scala code to make your build do things, rather than trying to configure some plugin that some guy wrote 5 years ago and abandoned on GitHub. Let's go through one by one. So first, the foolproofness. One aspect of Mill that's interesting is the fact that the performance is generally pretty good. And what's more interesting is you don't need to work for it the same way you have to work for the good performance in SPT or many other build tools. For example, Mill, we do benchmarks across other build tools. So we have benchmarks against Maven, against Gradle, against SPT. The SPT comparison is using the Gatling code base, where Gatling is a famous open source Scala load testing framework. So Gatling has an existing build, which is an SPT, and we ported it manually to a Mill build. It took about an afternoon. And the Mill build is not 100% complete, but it's complete enough that all of the Gatling code compiles, all of the Gatling tests pass, and it's enough for you to actually do real work with the Gatling code base using our new Mill build that took like 4 hours to write. So Gatling is not a small project. We're looking at 80K lines of Scala code, 800 files over 20 sub-projects. So it's quite a meaty project, like most of the projects we use for our benchmarks and comparison. So what's interesting about these benchmarks is when you start benchmarking SPT, you realize SPT has two different performance characteristics. One is its cold performance, where running SPT compile, SPT run, SPT test from the command line. And every time you run it, it spins up a new SPT server and runs everything from scratch. And this works okay, but it takes several seconds to get anything done. The second set of benchmarks is the hot SPT numbers, where if you open up SPT console, you run things in SPT console, then you get much better performance. Like for example, parallel clean compile of the whole Gatling code base is twice as fast in the hot SPT console, and clean compile of a single module is 10 times as fast in the SPT console as it is running SPT from the command line. But you pay a price for this speed in convenience. So you need to open your SPT console, you can run things. If you change a build config, you need to remember to run reload. If you don't do that, you'll be running stale config and your build will probably screw up. If you run something, it's taking too long, you run Control-C to interrupt it, you need to remember to go back into SPT console before you do things again. And so there's a bit of a dance here that you have to use to manage your SPT console in order to get good performance. And on the other side, the obvious naive way of using SPT, you get poor performance. So Mill isn't that much faster than SPT if used ideally. So you look at the numbers here, Mill's incremental compiles, no-op compiles, clean compile of single module. Even the parallel clean compile is off by just a few seconds. It's not like that much faster. But the thing about Mill is that Mill basically automates all this SBT long-lived process management dance for you. And it's all built in. So you just run Mill from the command line, and Mill will spin up a long-lived server for you, keep it warm. It will reload the config automatically when the config changes. If you kill the server for some reason, like Control-C, it will reload the server. And this all happens in the background. You don't need to install a separate build server or do anything to make it work or turn on the config. This is the default behavior, and it works very well. So that's kind of the point of what I mean by foolproof, in that with Mill, you don't need to worry about configuring a build tool or using a build tool correctly to get good performance. It's not fast in SPT, but it's just easier to get the good performance out of it than it is using a traditional SPT build system. Another aspect of Mill, which is easier to use and more foolproof, is the plugin ecosystem. So SPT has a very big plugin ecosystem, and that is both a blessing and a curse. It's a blessing because anything you want to do with SPT, someone's probably written a plugin for it, and it probably does more or less what you want. The curse is that in order to do anything with SPT, you need to go and hunt down a whole zoo of plugins and find all the right versions, find all the right documentation for right versions, and wire them up in your code base or your build system in order to use them to work on your code. So going back to the Gatling code base, which is what we use for comparison, Gatling requires 6 plugins to do assemblies, GMH benchmarking, Jupyter JUnit 5 testing, ScalaFix, Kotlin, Spotless auto formatting. And Mill also has plugins, but in this case, Mill only requires external plugin for ScalaFix. Assemblies are built in, we saw earlier, JMH, JUnit 5, Kotlin, auto formatting in all the different JVM languages is all just built into Mill. And it's not terribly complicated. It's not like the functionality built into Mill is superior to the functionality in the open source SPT plugins, but it's just easier to get started, where if you want to get started with the Mill project, you can just use Mill and you get 95, 99% of what you need built in without having to first go on a grand tour of the Scala open source ecosystem and assemble a Avengers team of all the different open source contributors and the plugins that they wrote. So that's about being foolproof. Next, let's look about what being understandable. So the two aspects I look into, one is IDE support. So I'm going to go back to code, and here we have the Gatling build for in mil and in SBT. Let me pull this up correctly. So here's Gatling build.mil file. This is the one we wrote for the comparison. Here's Gatling's original build.sbt file. And if you look at these two files, they're not actually that different. So for example, let's look at Gatling core. Let's jump to that. Gatling core here. So over here, we have Gatling cores config for both mil and SBT. If you can't read this, just let me know in the Discord or chat, I'll make it bigger. And what's interesting to first note is that these two snippets of code don't actually look that different. Like, sure, they have slightly different spelling. SBT says lazy val core equals Gatling module. Mil says object Gatling core equals extends Gatling module. The spelling is different, but in general, it means the same thing. So, they both are in the Gatling dash core subfolder. They both have dependencies on netty-util, on quick-lens. They both have dependencies on commons and JSON path, and they both have test dependencies on the last two. They both have settings on core Java dependencies, which is basically the same list in both. Let me pull this up bigger. Sorry, core dependencies, the same list in both. So given that it's so similar, like what's the difference here? You see IntelliJ has support for both SVT and mil. They're both Scala files, and you can kind of navigate around them. I showed you how to jump to core dependencies, and it works. So why do I say mil is better? The answer is what happens when you go slightly deeper than just poking around your superficial code base. For example, let's say you are a new developer, you don't know what library dependencies is. Or alternatively, you're an existing developer and you have to find how library dependencies really is used within your SBT build. Like, sure, you cargo culted some stuff of Stack Overflow, you read the docs, you're not clear, and you want to debug something, and you want to see, okay, I'm setting these library dependencies. Where is this data actually going? Who's using the stuff I'm setting? Now, these are obvious questions that people ask all the time in their normal application code, and they ask the same questions in their build code. So you may want to pull up documentation. You'll find that SBT and IntelliJ gives you nothing. That's the first kind of red flag. Next, you'll try and jump to definition for library dependencies, which does work, except it brings you to like a face full of decompiled bytecode. Okay, so this is, again, not great. Like, if you know what library dependencies already does, if you already know what library dependencies does, you're fine. But if you don't know, you're kind of hitting a wall here. There's no way for you to find out in your IDE what this key or this task or this workflow is doing. So what do you do next? Like, who knows? So what you typically do next, if you want to do it kind of statically, is you go to this magic file keys.scala in the SBT repository and grep for library dependencies. So if you know to search for keys.scala and you know that where to grep it, you'll find that it has one line of documentation declaring managed dependencies. So this is better than nothing. At least I know what someone said about this, even though it's a bit short. But what about what's next, right? Like, who's using library dependencies? Just now you saw it was someone was using plus plus equals. What's the value before the plus plus equals? And if you grep for it within this file, you can't really find anything. And the next thing you do is you go to the SBT project search bar, search for library dependencies, and somewhere in these 200 source files, you'll find where it's being set to. And that's really often how people figure out how to use SBT. And if you can't figure it out, maybe you're not smart enough or not experienced enough at SBT to do this, then you're in trouble, right? You're kind of stuck. You're hitting a wall where, sure, you can cargo cut what it means, you can cargo cut what some guy said on Stack Overflow or what was written in the docs, but there's no way to investigate what library dependencies does using an IDE. So let's see how mil is different. So mil is called IV depths instead of library dependencies, but it means the same thing. It's a list of dependencies it depends on. First, if you ask for the documentation, you get documentation. So any IV dependencies you want to add to this module in the format org :name :version for Scala dependencies, or org :name :version for Java dependencies. So okay, we're off to a good start. We have documentation. Next, you'll see that IntelliJ has this thing in the gutter which says IntelliJ knows that this is an override, and it knows who I'm overriding, and it knows where those overrides are defined. So we can go to, for example, the Java module definition, which is overridden, and see before I overrode IVDEPs, it is a task with empty aggregate, and aggregate in MIL is like a sequence of dependencies of deps. Okay, so already useful. Like now, I'm better than SVT in that just in my editor, I'm able to find documentation. I'm also able to find the default value of this task. What's next? I can go to IVDEPs. I can search for it. I can start finding where it's being used and trace its usage throughout the MIL build graph. IVDEPs here is used here in all IVDEPs. All IVDEPs is used in transitive IVDEPs. Transitive IVDEPs is used in resolved IVDEPs. Resolved IVDEPs is used in compiled class path. And compiled class path ends up being used in the compile task. So just like that, poking around my IDE, I'm able to navigate from my build to the setting that I'm setting within my build to how it's being used within the upstream MIL like build pipelines that come bundled in order to compile Scala. And you can go arbitrarily far, right? So here I'm looking at this compile task up in my upstream MIL kind of library code that my editor is showing me. If let's say I look at all source files, what's this? Ask for documentation. I can jump to it. You see all source files fed to the Java compiler. You can see the implementation right in front of you. It calls a lib.find source files and all sources. What's all sources? I can jump to that. All sources is sources plus generated sources. What sources? I can jump to that. Sources is the source path of the module, which is kind of like the base folder of the module and the SRC folder within it. So this is what I mean when I say MIL has better ID support than SVT and most other build tools. All build tools have some kind of ID support where you can jump to things, but often the things you jump to is not very useful. Here I show you SVT, but if you try and jump around the Gradle code base using IntelliJ, whether Gradle, Groovy, or Gradle Kotlin, you end up hitting the same thing. We're hitting these decompiled stubs that don't really tell you anything. In contrast, jumping around the MIL code base using IntelliJ, you're literally navigating up and down the task graph. So you can really see how these data, how these keys, configuration, and files that you're generating are flowing through your build code and ending up being used in the tasks that you need them in. So this is, again, nothing that is special to MIL. Those of you using IntelliJ in your application code are doing this every day in, day out, navigating around your Play framework website, navigating our HTTP4S web server, using these kinds of jump to definition and find usages. And what MIL does is that it brings the same experience to your build code to allow it to be totally transparent rather than being an opaque black box. So that is back to slides. That's ID support demo. The next demo I'm going to show you is the Chrome profile. So when you run something using MIL, it can take some time like any other build tool. So here's my Gatling code base in my terminal. Let me pull this up nicely. On the left, you see the Gatling build file. On the right, you see a terminal with Gatling loaded. I can do MIL clean and MIL _compile. So you can see MIL like SBT has a multi-line prompt that tells you what is running. The first time you run it, like compiling any SBT build file or Scala build file takes a moment. Then after a while, it warms up. So you can see in the bottom of this prompt terminal what it's doing at any point in time. Right? It's compiling Gatling Commons, core, compile. This may take a few seconds. After Gatling core compile finishes, it kicks off a bunch of downstream tasks, among them Gatling core test. Once Gatling core test finishes, you see even more tasks kick off after core test finishes. So just looking and eyeballing this prompt can get some intuition of what's taking up your time, but it's often not enough, right? You really need something more in order to make some actionable outcomes to improve your build experience. So what MIL provides in every single command is this Chrome profile. So this is a JSON file that tells you exactly which task started when on what thread, and alone is not very useful. Where it becomes useful is when you load it into this Chrome / tracing UI that's built into every Chrome browser you all have on all your computers. I bet you all didn't know this exists because most people don't know this exists, but it's very handy. If anyone needs an ad hoc profiler, you can feed in some JSON into Chrome comes built in. So I just drag my Chrome profile into Chrome, and voila, you see I have an interactive visualization of where my time in my MIL build command went. You saw I ran _compile earlier. Well, here you have Gatling compile taking up time, Gatling core test taking up time, Gatling commons taking up time, and so on. And what's interesting here, right? Like even if you don't know anything about MIL, even if you don't know anything about Gatling code base, you can already probably start having some ideas of what can be improved. Gatling core seems like a big bottleneck. Maybe we can break it up into submodules, smaller submodules that can compile in parallel. Gatling core test compile also seems like a bottleneck. And Gatling core test, it seems to be required before Gatling HTTP test compile starts. Do we really need to compile the entire core test suite before starting the HTTP test suite? Or does HTTP test really just need a few core like test helpers that can be broken up into some Gatling test utils library that compiles faster and will allow all this stuff on the right to move further to the left? So this is the kind of thing that Mill gives you by default. And although other build tools in theory could give it to you, in practice it's difficult to set up and you probably won't do it on a day-to-day basis. Like for SBT, you can probably find a plugin to do it. For Gradle, you might need to go pay for Gradle Enterprise build scans and go hook up to the Gradle Enterprise backend to web services. In Mill, it just gives you a JSON file that can load into any Chrome browser that you all already have and immediately start getting actionable insights about the runtime characteristics of your build and what's taking up time and what you can do about it. So back to the slides. That's the understandability angle, the ID support, introspection tools. Lastly, let's look at extensibility. So most build tools require extensions we publish as plugins. You want to do foo, you need the foo plugin. You want to do bar, you need the bar plugin, so on and so forth. You don't have a foo plugin, you need to go write one. You go learn some plugin API, plugin framework. The bar plugin's abandoned because some guy wrote it 5 years ago and hasn't updated it. You need to go bring up the bar plugin up to date. Mill does have plugins, and yeah, I showed earlier, for example, Scala Fix is a third-party plugin, but you don't need them as often because Mill lets you write code and import any Maven Central library to use in your build scripts. And let me show you an example, right? So over here, I have, let me bring this up. Over here, I have like the minimal Mill build file for Scala. So this is object foo extend Scala module with the Scala version and nothing else, right? I can compile it, foo.compile, and it works. But let's say I want to do something custom. Let's say I want to include the line number, the line count of my module as a resource for the file, for the application to use at runtime. So this is a bit of a synthetic example, but kind of representative of all the weird things that people need to do in their builds in realistic applications. Maybe you need a bill of materials to publish for security purposes. Maybe you need some custom build metadata to publish with your production Docker container for debugging in production. Maybe you have some special IDL that your company uses. Maybe you need a protobuf compiler or a thrift compiler to generate code. There's all sorts of requirements that people end up needing in real builds. And so while you can sometimes find plugins for them, often these are very bespoke and very unique to each individual business. So back to our line count functionality, right? Let's say I want the line count as a resource file to use at runtime. In Mill, adding a new task is just using a def, let's say line count equals task. I can add documentation, like say counts the lines of code in this module, and I can start using the other tasks in this module to compute this line count. For example, if I want to count the source files, source lines, I need to go for all the source tasks. I can use IntelliJ to pull up the documentation. It looks like I want all source files, which is all individual source files fed into the Zinc compiler. But I can see documentation for all the others if you're curious what they do. Call it because it's a function. Can map to get the references, path references. I can read their lines. I can get the size of the lines and I can sum them up. So this is all you need to do to write a Mill custom task. Now that I have this, I can do Mill show foo.line count. See, line count is 17, which is correct. If you look at this, it says this is 17 lines of code excluding the trailing new line. I can inspect foo.line count. You can see that, yes, it's called foo.line count. It is in build.mill line 8. That's what you expect. You can see that it has my Scala doc, including the typo, the lint of the code in this module. The dependency on foo.all source files is captured. You can inspect it from the command line. And this is everything you do with getting SBT build as well. But with Mill, it's just so easy to write any normal method and turn it into a task. Just wrap it in task and curly braces. So now I have my line count task, but how do I wire it into resources? So Mill resources are handled using this resources task. And you can search for it. You can pull up the documentation. It says the folders where the resource files of this module live. So I can override it, say override def resources. I get autocomplete even. I override it as a task. And I say os.write to the task's destination folder, line count.txt, let's say line count.toString, format this nicely. And I'm going to say super.resources plus plus a path ref to my task.destination folder. So every task in Mill gets a destination folder by default. That helps us keep things from having side effects that collide with other tasks. We call it task.desk, desk. And now I've overridden my resource folder. I can show my foo.resources. It has both custom Scala / foo resources, these original super resources that comes built in, but also has this out foo resources.dest folder. And this is a custom task desk folder that I'm appending to my resource path. If I look inside this resource.dest folder, you'll see it's line count.txt. I can look at line count.txt, cat it, you see it has a number 17. And now when I mill foo.run, you can see it's able to load the line count from line count.txt at runtime using these Java class loader get resource as stream APIs and print it out at runtime. So line count's a bit boring. Let's do something more exciting. Let's say I want it as not the text file with the number, but as a HTML file. So Mill doesn't come built in with any HTML templating library. You can see this doesn't work. You can run it in the terminal, IntelliJ, iTerm both tell me Scala tags doesn't exist here. But Mill allows you to import things very easily. So you can just say import $iv, which pulls things from Maven Central, and just say com.li Scala tags 0.13.1. Now, if I reload my project, give it 5 seconds, you'll see that now IntelliJ is able to recognize Scala tags.txt. You see that my terminal is able to run it and compile Scala tags.txt. And now I can define my new task, line count HTML equals task. Who, let's say it's a div with h1, line count, and a key of the line count value. And I render it as a string. And bottom, instead of using line count, I use line count HTML. And now when I run foo.run, you see that my application code now gets a HTML template as a resource that I can print out and otherwise manipulate at runtime. So again, like rendering a HTML file with a line count is kind of a silly example, but it's kind of representative of all the weird things that real world builds and real world projects end up needing to do. And you end up not just needing to write code, you end up needing to use libraries from Maven Central, because that's the libraries you're using in application code that you want to use in your build code. And with Mill, not just writing code with using reading files and from disk and counting the lines is easy, but even pulling libraries like Scala tags from Maven Central and using those in your build is really easy too. And there's no Mill line count plugin or Mill Scala tags plugin here. You just import the libraries and use them just like you would in any Scala code base. So that's this plugin-free extensibility that Mill provides. You can directly write code or use any libraries, both of which you already know how to do because you're Scala JVM developers. So that's a quick tour of why Mill, because it's foolproof, because it's understandable, because it's easily extensible. For the last few minutes, let's talk a bit about how Mill works. There are 3 sections here that I'll go through in turn. First, the idea that in Mill, modules are just objects and tasks are just methods. So when it's on the left, you see this minimal foo Java module. And unlike a Scala module, you don't even need to specify a Scala version for Java modules. And object foo is literally a Scala object, and Java module is literally a Scala trait. And like any object inheriting from a trait, you inherit all the methods. Like in this case, a simplified version is sources, compile, class path, resources, and assembly. And they call each other. The data flows through, like the sources get passed to compile, get passed to class path, get passed to assembly, and so on. You already know how method calls work and call graphs work, and you know how inheritance works. So this should not be surprising. When you start doing custom stuff in your Mill build, for example, defining your line count, depending on all source files, and defining resources, overriding the previous resources, calling your line count, but also calling super resources, this adds methods to your object, just like any other method definitions with overrides and supers does. Like you already know how override and super work, so this behaves exactly like that. And it results in the build graph looking like this, where I have foo sources being used in line count, and foo resources, which still uses the super resources, and both resources and class paths still being used in assembly. So once we have this graph that Mill captures, Mill is able to automatically make decisions around parallelization. For example, it knows that the blue task can run in parallel with the red tasks because they don't depend on each other. But assembly in green needs to wait for both blue and red to finish because it does depend on both. Mill allows you to automatically Mill helps automatically cache all your task outputs to disk. So Mill, for example, knows foo.line count has a name foo.line count. So you can say, I'm going to cache it in out/foo/line count.json as using the upicker library. Similarly, foo.compile gets cached out/foo/compile.json with files being put in out/foo/compile.dest. Similarly for assembly, where the metadata goes to a JSON file and the files go to a dest folder. This is a task.dest folder we saw earlier. When you make changes to inputs, for example, you change the resources folder that is now called super.resources, Mill is able to just do a simple breadth-first search in this graph and say that, hey, resources is downstream of super resources, so this needs to reevaluate. Assembly is downstream of that, so that also needs to reevaluate. On the other hand, line count, compile, class path, none of these are downstream of the changed inputs, so we can just reuse the cached JSON, which was generated automatically. So what's most interesting about this whole setup is that you look at the code on the left, there's nothing here related to parallelization, caching, introspection, invalidation, and so on. You don't see anyone computing cache keys. You don't see anyone writing things to disk and deleting them on disk. You don't see anyone taking locks or having semaphores or spawning threads or futures to parallelize things or actors. None of that occurs here. Like the code on the left is literally pure business logic. I'm taking the line count is all source files, reading the lines, summing them up. Resources I'm overriding, I'm writing out the text file as a resource and I'm returning it as part of the resource path. So Mill does all the other things for you. And this has two advantages, right? So one is it's much easier to write the code. Like you can do the stuff, even a new grad who doesn't know anything about Scala can probably fumble through the stuff on the left and more or less get it working, which cannot be said for equivalent SBT or Gradle build. The other thing is that because all this stuff is automatic, it happens much more aggressively than it does in SBT, Gradle, or other build tools or Maven. For example, line count here is cached. In this case of line count, it's kind of trivial, right? It runs very quickly. But I'm sure many of you have SBT builds where your code generator runs every single time you run a command because you didn't bother to put in the effort to cache it because it's not automatic. Or maybe your resource generator is always hashing and always reprocessing resources because you forgot to cache it. In Mill, that never happens because everything is cached automatically. And therefore, in any large Mill build, it typically ends up being a lot faster than your SBT or Maven builds, just because all the miscellaneous utility tasks you end up having are cached and parallelized without having you do anything. So that's this modules, objects, tasks, and methods idea. The next bullet point is how this actually is implemented under the hood. So if you look at this def IV depth here on the left, you'll see that, okay, def IV depth is an aggregate, which is I can seek with some Scala doc. There's a IV string interpolator, Scala organization, Scala reflect, Scala version. So this is just pulling in the right Scala reflect artifact for whatever like Scala version you're using, right? And you can show it, you can inspect it from the command line. It prints out the name, file, line number, all this stuff. We may wonder, like, how do we get this information at runtime? You don't normally get method names at runtime. You don't normally get the file name, line number at runtime. You certainly don't get a Scala doc at runtime. I mean, you have a method that calls other methods. You can't just look at the inputs at runtime. So what's going on here? So what's going on here is that when you write the code on the left, it expands into this code on the right. So, and it does this through a whole range of different techniques. So we have some build time code generation like Scala CLI or Ammonite or the Scala REPL does. For the Scala doc, we have a compiler plugin that grabs the Scala doc, puts it in a Java annotation, which we then use Java reflection to fish out at runtime so we can print it out. In order to get the inputs here, so you can see what methods this IVDEPS method calls, we then have a macro implicit conversion that turns this direct style, so-called direct style method call, into a applicative functor zip map data structure. So most of you are probably familiar with monads. Few of you probably use applicative functors on a daily basis, but they are like a less flexible version of monads that allows you to therefore manipulate and analyze them more easily. For example, applicative functors let you statically analyze the dependencies without having to evaluate them, whereas monads, you have to evaluate them first. So for Mill, I want to be able to look at what my build graph looks like before evaluating my build, and so I use an applicative functor, which then their operation is normally called zip map or app, depending on what background you're coming from. Line number, file name, and the name of the method itself all come from macro implicit parameters. from the source code library, source code line, file name, and name. And the JSON serialization comes from the uPicker library as a normal implicit type class. So all this seems like a lot, right? But the thing is, when you are writing mil code, you write this. And generally, all the other stuff just stays out of your way 99% of the time. 1% of the time, you may need to worry about something to do with that, but vast majority of the time, you just write your easy code. You get the nice stuff on the bottom left, all the introspection, parallelism, caching, and validation for you. And only the mil maintainers need to deal with this mess of complicated techniques and implementation details. So that's how it is implemented. The last thing I'm going to touch on before we finish the talk is the use of the direct style DSL instead of a staged DSL. If you look at the difference between the mil file on the left and the equivalent SBT file on the right, you see that mil, they're both Scala. SBT is not more verbose than mil. Mil is not more concise than SBT. But what's interesting thing is that the mil code on the left looks like the code you write on a day-to-day basis with objects, extending traits, with definitions, Scala doc, imports, packages, and so on. The SBT code on the right is technically Scala, but it doesn't look like any Scala code you've probably touched outside of SBT code base. You have these lazy val line count equals task key things with this pseudo Scala doc that's not really Scala doc. And line count is kind of a method definition, but it's not really a method definition, it's actually a lazy val, but it's used like a method definition. And the type signature here looks different from a type signature here if you're using a colon, if I put one. And generally, all this stuff on the right looks like Scala, but it actually isn't really Scala. And therein lies a problem with a lot of SBT tooling and SBT, I guess, intuitiveness and understandability. So if you look at this from like a multi-stage program point of view, SBT is really two programs. One is the stage one program using Scala lazy vals, Scala method calls, Scala strings, and other data structures that evaluates. And for this first program, IntelliJ has no problem navigating around your defs and vals and other helpers within your build file. We saw that earlier in our Gatling example. The problem is this first program is not enough to actually understand what your build is actually doing. Your first program, all it does is construct a data structure that is interpreted later using the stuff in the top right. And the stuff in the top right are things IntelliJ does not know about. IntelliJ does not know about file function.cache to cache your task outputs. IntelliJ doesn't know that task overrides work differently from Scala method overrides, or that settings lists work differently from Scala traits. IntelliJ doesn't know about the details of how subprojects work and how they differ from normal objects in Scala. So although SBT is not nominally written in Scala and is using a Scala DSL, the Scala part of it is honestly the less interesting part of it. And when you jump around it, it doesn't tell you anything at all. And the more interesting part about it, for example, how the four-dimensional config scope hypermatrix works in SBT, that stuff is totally outside of Scala and therefore totally outside of the expertise both of IntelliJ and VS Code as tools, as well as any Scala developers that you may be employing in order to work with this build. Like your Scala developers know the stuff down here, your Scala developers don't know the stuff up here. So Mil does this differently. Mil, rather than having a two-stage program that you run some Scala during the program that then gets interpreted later using some more different techniques and concepts, Mil works very hard to just squeeze everything into the first stage. And we saw that earlier, right, with the crazy code generation, macro implicit conversion, applicative functor transformation thing. We saw it with the compiler plugins, grabbing the Scala doc to put it available at runtime. So all that's honestly a bit crazy. And it takes all that work to squeeze all those concepts into stage one of your Scala program. But the benefit now is that once it's all in stage one, it's stuff that IntelliJ, VS Code, and your day-to-day Scala developers know about. Your new grad who took Coursera Scala knows how override works. Your Java developer who fresh out of school knows how super works. It works the same as in Java. Your methods are your tasks are just methods. Your call graph is your task graph. Your objects are just modules. You all know how reuse via traits works, stackable traits, abstract methods. All that's exactly the same. You're all already writing Scala doc, hopefully, so you don't need to learn this new docstring syntax. And this is what really makes Mil so much more intuitive, not just for humans, but also for tools, in that it squeezes everything into the first stage of your Scala program. So Mil programs, despite all the magic, look like Scala and behave like Scala. And this is something that SBT and many other frameworks I think, have problems with. Not just SBT, but things like Cat's Effect, sometimes Zio, Akka Streams. They all have this two-stage evaluation model where the first stage in Scala is great, but someone needs to go teach IntelliJ about the second stage, otherwise you get no help at all, and because IntelliJ only knows the stuff in the bottom right. So that's how mill works. Just to wrap up, I think I have 1 minute left. We talked about what is mill, why use mill, and how does mill work. I won't repeat all this. You can read it yourself. There's more documentation online at millbuild.org if you want to get involved. And I think hopefully you found this interesting. And if you want to get involved, we can all work together and make a better build system for the Scala community going forward. Thank you.